In our previous example, we saw that the velocity of the falling object with respect to time, that's vt, is equal to some gravitational acceleration multiplied by the mass of the object, divided by our drag coefficient, and that all multiplied by some functional form in the brackets on the right here. Now this equation represents an analytical or exact solution, and the reason why we call it this is because it satisfies the original ordinary differential equation exactly. Unfortunately, this is not always possible, and as engineers we have to develop new methods to solve complex ordinary differential equations. And this alternative method is what we call a numerical solution. A numerical solution approximates the exact solution of the partial differential equation, or ordinary differential equation, and this requires reformulation. And we're going to try and visualize that from our previous problem, that is the falling parcel. And we're going to do this using Newton's second law. So again, if you recall, the acceleration is some function of the force, or the resultant force acting on the object, and its mass. In this instance, it's just the resultant force divided by the mass. And we know that the acceleration, a, is just the time rate of change of velocity. So it's just the time rate of change of velocity. And this in turn can be written as delta v over delta t. And this is because our time step is finite. So what this means is that the difference in the difference of the velocity with respect to the difference of time, which is our acceleration, is proportional to the force divided by the mass. And we can again rewrite this to the velocity at time t of I plus 1 minus the velocity at our current time step divided by our future time minus current time. Now, v of t at time I is our initial velocity, and the velocity at our next time step is called, v is defined here at, let's just highlight that, v at ti plus 1. The denominator here represents our step size, or the difference in time. And as I've already mentioned, the reason why we can approximate the derivative of velocity with respect to time as delta v by delta t is because delta t is finite. And if you remember from calculus, if delta t is finite, in other words it has some value, then the derivative of the velocity with respect to time equals the limit. So the derivative of velocity with respect to time equals the limit of delta v over delta t as delta t approaches 0. Now we can apply this to our analytical solution from before and approximate the acceleration accordingly. So for us to do that, remember we said the acceleration is just the velocity at our next time step, ti, divided by t of I plus 1 minus ti, and that's equal to, we said, the force, the resultant forces divided by the mass, and in this case that turns out to be the gravitational acceleration minus our drag coefficient divided by the mass. And we can then reshuffle this around to get the velocity at our next time step, v of ti plus 1, being equal to the velocity at our current time step plus our acceleration due to gravity minus the drag coefficient divided by mass, and that all multiplied by our time step, t of I plus 1 minus t at I. Now hopefully this looks something familiar to what you've seen before. Here we have the new value of the velocity being equal to the old value, so the new value of the velocity, v at ti plus 1, equals the old value plus some constant multiplied by our time step. Now this represents a simple linear equation where the new value, we can write this as the new value being equal to the old value plus the slope multiplied by our time step, delta t. And this is formally called Euler's method. So now let's apply that to the falling parcel.